Get it started again. The rest of the folks will hear us having fun and come in. All right, so we've covered the two easy things about plant construction and IBR components. So we'll get into the more fun details here, which is actually kind of fun to talk about. So, and again, we're talking about these kind of components here, so we keep them in mind as we go through the modeling pieces and aspects. But it's just really important to just fundamentally for modeling as we go in here. But all these things will apply to the EMT also. So main IBR transformers are a big difference from what we're used to for synchronous machines. We're just calling them main power transformers. It's easier when a synchronous machine because there's just one giant transformer, but there are many other ones in an IBR plant. But we're calling the main power transformer the main power transformer because it's the main really easy naming convention. So the other thing to keep in mind, especially in the EMT space, in one way, but also ignore it in the other, is that the main power transformers often have on-load tap changers, which are also a control device. If you're running a simulation long enough, you may see interactions and controls between the on-load tap changers and the rest of the plant controller. Typically, on-load tap changers are 30 seconds to 90 seconds as far as tap time. So if you're running a simulation that long, it may be worth it to include a tap changer in there if that's something that you're worried about studying, right? Or if it may act. So that's another one of those things about know what you're studying and how long you're studying it and how you're testing it. Because if you're running a 10-second simulation in the EMT or the PSPD world, you're never going to see a tap changer movement, right? But if you're running a longer one, or if you're doing like a voltage study or something like that, very important for control interactions too, in that case. So the transformer characteristics are really, really important. Obviously, right? They're determining what the losses are, how they're operating, the deadbands, the tap times, the impedance spaces in different softwares are maybe different, maybe default to different values, or maybe specified only and not have a default value. Or if we put the wrong value in, it might have its own default depending on the software. So this is one of those things when you're building your EMT model from other data, to be really cognizant of where you're getting the data from, right? If you're getting it from transformer factory acceptance test cut sheet, you'll have probably a number of different impedance values at different impedance spaces. You have to be careful which one you pick and make sure that you're putting the right base into the EMT software or the transformer model to make sure that the impedance is what you need it to be, right? If you put the right impedance number or the wrong base, you're going to get a wrong effective impedance. The other nuance that we really need to focus on, because we're going to talk about benchmarking between the EMT and PSPD models a little bit later, is that some softwares have default bases for impedance, which means some people, when they're building their models for the first time, will put everything on the default base and not a different base. So for certain softwares like PSC or other PSPD softwares, usually 100 MVA is the base. So also to keep in mind is that the base for impedance is not the rating of the transformer. Sometimes they're similar or the same, but when you're going through and you're trying to figure out the size of your transformer, the size of the transformer will be an MVA value, but it may not be the impedance base that you're using. So just keep that in mind and keep that kind of in your mind as you go through. We'll talk about kind of common sources of error when we talk about PSPD and EMT model benchmarking. But these are one of the components where it's really easy to get stuff wrong. And that's both manually and also for automation purposes, even between two different PSPD softwares, automation purposes. Like if you have a script that tries to take a transformer representation and a .raw file and put it into two different softwares, you may get two different transformer configurations. The right data might be in there, but in different wrong spots. So really, really prone to error because of the way that there are many different parameters, and also they're laid out differently and bases are different. The representation of transformer steps and deadbands and size and operation range is pretty different among different softwares, and a really big source of error. So the other thing to keep in mind, some characteristics you might need for an EMT study, like transformer saturation specifically, you're not going to get. You probably don't have that. It's probably not in a factory acceptance report. You may ask for one, Lucas, how many times do you ask for a transformer saturation and actually get it?
Yeah, occasionally, if we know it's gonna be a part of the scope to study something that you need the transformer saturation, then we'll get it. But like we're getting more instances in series compensated networks where subsynchronous ferroresonance is a real problem. And for those studies, you need that information. So I think it's just kind of part of the initial data request. So then, yeah, you get those test reports that have that. But if those tests weren't done for a transformer, then you're basically out of luck unless they can pull data for a similar or proxy transformer. So, yeah. But majority of the time, we are using typical saturation data.
That's just, yeah, one of those things that's very difficult in the IBR world, especially just given the nature of how these plants are constructed, because of the stakeholders and the money to be made. Very often, or my experience previously, I'm not sure if it's still experience, but sometimes you have a transformer laying around and you want to use it for a plant and you're putting as many inverters behind that transformer as possible. And as you load that transformer closer to its max, you have obviously more propensity to saturate that core, and have those values be really important. I mean, I've done studies where, we spent months trying to figure out a controller issue, and the issue was that the transformer saturated and things went weird. So it's really important depending on the study, but it can be difficult to obtain. But just keep it in mind when you're going through that kind of process of what am I studying and why, picking the data. So this is, I'm using a word I hate here because it's the IEEE word, but this is supplemental devices. So in the IEEE world, supplemental device is basically anything that's not the inverter. Little generalization there, but that also means that the plant controllers are supplemental devices in the context of IEEE. In defiance, I split plant controller into a different slide, so we can talk about those separately and give them a little bit more attention, but they're actually kind of similar in a lot of ways. The discussion is very similar for supplemental devices, but basically these are fixed shunts that are there, simple fixed shunts. They're just doing something on their own. Switch shunts that are communicating with the rest of the plant controllers, which leads themselves into kind of complex controller interactions and, maybe a main controller with the plant controller and a secondary controller with fixed shunts to keep you in nominal ranges. A lot of different possibilities with these supplemental devices there. And it really underscores the importance of doing an EMT study, because these complex controller interactions and logics and step changes and sizes and things like that. One, good to have the level of detail in the model. And also when you're doing things like switching operations as part of your normal operation, you're getting fast transients of voltage. And another thing, which is really good to have studied in the EMT. I mean, a lot of EMT studies are to study exactly those types of phenomena. So for two reasons, if there's a lot of supplemental devices at your facility, EMT is a good tool to use there. So, and also a way to maximize the benefit if you're deciding to do an EMT study is to really maximize the lower hanging fruit in the EMT software, which is modeling communication and protocols by doing time delays, sample times, round trip communications, things like that, because the more supplemental devices you have, they're probably all talking to each other, which means the more complexity the signals are, or how complex the signals are, and the longer kind of round trip time you may see. So very important to keep track of what's there and why it's there. A lot of times, especially the PSPD world, there's facilities that have, a MSU, a mechanically switched unit scheme, and there's no models in the PSPD. No one's putting a switch shunt model in their PSPD. There's certainly not, I mean, you can in some user-defined models, but it's very rare and hard. And even for me, when I was doing it as the manufacturer who knew the model, it's very hard to make those types of things work in PSPD. Much easier in the EMT, so it's a good way to bridge the gap and study those things. And that same thing goes for kind of controller hierarchy and communication. Who's the main controller? How do they talk to each other? Does this combination of equipment mean I need a separate piece of equipment that adds more communication time? And a big consideration here when you're doing this is that the more devices means probably the more manufacturers or vendors you're dealing with, which means more stakeholders, more people to ask questions and get data from, mitigating and managing the different data security needs of folks who you're working with. If you're doing a mixed manufacturer site, you'll find very quickly that the manufacturers don't like each other very much. So kind of try to get the right data out of them can be tricky, especially with multiple vendors there. So moving to the collector system, very widely vary. They vary widely among different types of IBR plants, but the general layout's the same. The big difference is the collector feeders and cables change. Collector system for solar PV and a collector system for a BESS look pretty much the same, even with the lengths. Collector system for a wind farm may be completely, same configuration, but much longer, much more branching, long cables and lines and things like that. So the main components, collector buses at the substation, cable sections and junctions, protective relays. We talked earlier that protective relays don't always have a good proxy in the EMT world, so you're probably still using a generic protection there. And this is where we talk about how much level of detail do you want to put in here, right? Do you need a full frequency representation of a short cable in a feeder? Maybe, depending on the study. So it's one of those things to keep in mind just in general when you have the problem modeling all these sections. A lot of the times, especially if it's an aggregated model, you're using a pi section a lot of time. But outside of the simulation, this is another place, especially the main power transformers, where it's really easy to mess up. The first step to building a model like this is usually building a disaggregated model by connecting in a script or a tool or a spreadsheet or something, or even in the GUI of the software. You're literally manually inputting all these cable sections and the cable types and the connection types and things like that. And that, for a wind farm, that could be a few hundred segments. And if you're doing manual work like that for that much time, it's really easy to make a mistake. And this is another one of those situations where you get a lot of wrong data. You get different versions of different drawings that have different cable lengths for the same plant. Another place where you get a little bit of insidious errors with the automation scripts, because you can very easily make a couple mistakes in the collector system and the script will run just fine. And the impedance is okay, right? It's in the range of acceptance, but it's wrong still. So it's hard. It's a lot of opportunity, a lot of manual work, and the problems might not be super clear when they come out of it. So that really, collector system seems simple because it's just cables connecting stuff together, but it's, again, one of those things where you really want to have that due diligence at the beginning. And also, when you're kind of transposing collector systems between softwares, keep in mind the base changes in impedance and how you're changing the model representation as well. So on the collector system here, so again, for modeling the lines in EMT, there's a bunch of different ways to model them. Choose, I guess, which one sounds best. Lucas, do you have any kind of guiding principles on what to use? Or
yeah, like I mean, for a equivalent collector system, probably the Bergeron line would be the one I would go to if it's long enough to do that. If it's a very short section, then the pi section. It's again, you're taking something that's a potentially complicated collector system and lumping it into a single line, and it's we know that that's not exactly how it looks in reality, and we're missing some things there. But yeah, if you can put a Bergeron line there, that's probably your best bet. I don't think a frequency dependent model makes any sense.
you said you use length as a qualifier. Do you have a length in mind?
I mean, it's going to be probably based on your simulation time step, and the sort of like effective travel time across the line. So you can take the X and the B of the line and figure out the propagation delay across the line, and if that's longer, you'll model it as a pi section or Bergeron based on your time step, and whether it's longer or smaller than your time step, which we'll probably talk a little bit more about tomorrow as well when we talk about system modeling things. But
thank you. Any questions on the collector system? The inverters, the fun piece of the IBR plant. So when we talk inverters today, or when I talk inverters, I mean everything the OEM provides, which might be more than an inverter. Could be the inverter and the generator step-up transformer, the inverter step-up transformer, just because that's the equipment the OEM is responsible for, the manufacturer is responsible for, so I put them all in the same category. So you may see two different representations. One may have an actual step-up transformer in there. In the EMT world, it may be more of a, I guess, a scaling transformer where you can actually put in, you'll have a, number of inverters in one representation of the inverter, and then you can select a number of inverters in the actual transformer, and that'll actually scale a transformer up and do the calculations for you to basically equivalentize X number of transformers in your configuration. So there's different ways that you'll get these models from folks. Some of them have the step-up transformers there. Some of them don't. I'd say most of them have a GSU inverter step-up transformer. There are some manufacturers just lump it all into one component that connects directly to 34.5. So it's not to say that if you don't see a GSU it's automatically wrong, or an inverter step-up transformer is automatically wrong, but that's a red flag to dig into. And as you do that a couple of times, you'll learn which manufacturers do that and which don't. So in the steady state world, so like setting up the load flow portion of the EMT, really simple. I have an inverter representation. The manufacturer gave it to me. I'm going to just type in either a multiplication of the base times however many inverters, or there's a field to put it in there. And the linking is on the side of the EMT software. It's linking to the models if you put the hierarchy together. So the steady state's pretty simple. For the dynamic piece of the EMT, this is where we talk about all the parameters you have to test and tune at the inverter level. So the little nuance here specifically is a lot of, or the vast majority of the testing and tuning that end users do. And I say most end users, not like the Lucases of the world who are doing really highly specialized studies all of the time. You don't do a lot of tuning at the IBR level. You may be changing ride-through gains, but a lot of the other parameters at the inverter level are things like capability parameters and current limits and recovery parameters and things like that, which are the vast majority of the time better done with the OEM's guidance and things like that. So there are a lot of parameters that you'll see, but if you think you have to change something in the inverter to test or tune something, keep in mind that most of the time those settings need confirmation from the manufacturer, because even changing a ride-through gain, which when we see gains and stuff, we usually consider gains the tuning value, just in general. But changing a gain in the ride-through could lower a current limit, it could change your current limit, it could change a time constant, is all nuanced and things like that. So those are some things you might want to ask for in a user manual or a documentation, is kind of some guidance on tuning. And the inverter level, you're going to probably see varied success. You're going to get varied success getting those values. Some will give you a really detailed thing that says, here, you can change these values between, or these parameters between these values because of the way the controllers are set up. You may also get a blanket, please don't change anything without telling me, because everything's intertwined. So really important to keep in mind and not to be fooled by the simplistic nature of just like dropping it in there and plugging it in. That the dynamics piece, all the parameters are extremely important. And even if you can change them to change your response, that you really need, at least for these parameters specifically, probably need manufacturer sign off. And this is where things should get caught before you put them into the actual field for safety reasons. So it's also really important to know what you're getting, especially in the EMT world. So in the PSPD world, when you get a dynamic model, it's in a separate text file, right, or something in a different format. If you're getting an EMT model from an inverter manufacturer, you may get something that has an example collector system in there. So you may get an inverter, in a step-up transformer, an example pi section, an example transformer, an example pi section, and a single chain infinite bus. And you get those just so that you can kind of run it out of the box and see if it runs the right way. But that also looks a lot like an aggregated real plant model, right? So it's really important, and this is an EMT specific nuance here, is did I get a plant model or did I get one of the example models? And this is something that gets missed. It sounds really simple, right? But it's something that gets missed a lot of the time. Because how do I know, unless I've seen 10 models from manufacturer X or seen 10 models from consultant Y, what they should look like, right? When an aggregated model looks pretty much just like this all the time, right? They all have the same components. It's hard to check. So you can ask that question, but also they might be confused as well. So there's been many instances where I've said, is this site specific? And they say yes, and then it's default. And I know it's default because I built that and I sent it to you. So it's one of those things to really keep in mind. But one thing to help is that really there's no two identical IBR plants. There's never, that's a hard statement, but there probably will never be two exactly the same parameterized models, ever. There's site-specific tunings, collector systems are different sizes, different number of inverters. So if you get two models side by side from the same manufacturer and they're identical, they're probably both example models, or someone copy pasted and they're still not a plant model. So something you don't really have to talk about in the PSPD world, but it is confusing and misleading a little bit in the EMT world for this. So the other things when you're getting inverters, and this is like, it sounds super simple, but these are mistakes that happen all of the time. Is it the right equipment? Is it the right manufacturer that you chose? If I know I'm working on a manufacturer A plant and I get a model from manufacturer B, I'm going to ask a follow-up question to see if this is what you meant to send me. In that type of situation, that's a little easier to catch. Is the software version correct? Really difficult to understand and to know. And you may not know, really. Because if I'm a developer, I might not know what firmware is getting put into the final project. I might know what model I have at the time, but that's another important question. And one of those things that you'll kind of, as you get through here and start doing this a lot, you'll notice things, right? Like, so if I get a model in 2025 for a new plant, and I know that this manufacturer labels their software versions in some way, and I know that versions from 2015, probably there's a mismatch of communication there, and I'm digging into that to check. One of those spot checks that leads you into detailed checking. And does the model that you have gotten, does it include all the things that you're expecting? All the components, all the manufacturers that you're expecting? If you know this is a complex plant with two different manufacturers of the inverters and a supplementary controller, and it's just one inverter manufacturer model and one inverter manufacturer PPC, another red flag to dig into. So while it seems like a simple thing in the EMT, I got a model from the manufacturer, I'm running it, or I got a model, I'm cutting and pasting it. There's a lot of other considerations just to make sure that you're not just starting from completely wrong starting point. So plant controllers, not supplemental, very important. Sometimes the main controller, most of the time, main controller of the plant. They're doing all the normal operations. They're coordinating the plant-wide performance. They're getting out of the way during ride-through and picking up the communication and controls after the ride-through. They may not, you're not going to see this in a steady state model like in a load flow. You will see it in the EMT, right? You'll see a block for a plant controller because they're kind of conjoined, the load flow and the dynamics piece there. They may be standalone. They may be part of a multi-PPC control scheme. Know what you're looking for and what you're trying to see. But it's also coordinating all supplemental devices, right? So if you have a plant controller and a bunch of capacitors at a facility and the plant controller is not connected to the caps, maybe they're fixed and that's how they operate, or maybe they're missing a connection. Another red flag. So they dig into make sure you're modeling correctly. And also just very difficult to manage multiple OEM and control vendors just because they all have different protocols, different models, different modeling practices. They might not talk to each other in the model space, things like that. So it's really important for the plant controllers because of the way that they're handling most of the normal operations to get high quality documentation from the manufacturer. Because these plant controller parameters, for the most part, are the ones you're tuning for your site. This is where the voltage schedule is. Your voltage deadband is. Your frequency droop is. Your frequency deadband. The normal operations. Your voltage set point that your utility sends to you. They're all here in the plant controller. And if you're trying to use a model to kind of ensure that you're setting your controls up to stay within a deadband or a voltage schedule given by the utility, you should know how the parameters are getting used in math, right? So the good documentation has basically, control function, how those values are used, what parameters are used in the controls, and what the values and units are. basically, and how to set up your measurements and where to set up your measurements are really, really important for the documentation piece. Yeah.
A little bit more about the multi-PVC control scheme. I've seen that in more models, and they thought it might have been an error. But is it essentially one behaves as master and the other slaves?
It could. That's one of the reasons why EMT is good, that you can basically model them however they're modeled in real world, or however they're connected in the real world. And a main secondary kind of hierarchical control is one method that people use. That's what I would use. What could, because then you have one measurement point, one plant controller doing the math and just sending signals to the other one, who's sending it to their inverters. You may also, in weird cases, have two independently operating plant controllers, which if you're in the PSPD generic model world, that's what they all look like, because you can't model that in the PSPD or with a generic model. You can't, there's no main secondary mapping, right? So this is one of those situations where it's really critical to have the EMT and do the modeling of the actual communication in main and secondary hierarchy. But if you see two, it doesn't mean it's wrong. This is common and increasingly common.
What are the benefits? I guess I don't understand why you do that.
Does the developer want to answer why use two manufacturers before I give a bet? Yeah, go ahead.
Well, sometimes you get from the energy storage provider, they'll have their own EMS controller. And so they would have equivalent of their own power plant controller for the BESS. And then for the PV, you are getting PV from multiple different inverter manufacturers. Whether you're getting a power plant controller from them or a third-party integrator, they'll have their power plant controller and their power plant model. Then you might have above all of those, a master power plant controller that's coordinating both PV and a BESS component. And its dynamics that might be at play too.
Thanks. Any other developer insight into why? Other than that, it might be cheaper to get two different manufacturers on one site?
That's the obvious one. Two different manufacturers. Availability is another one. You bid in a project and you don't have the available turbines from one manufacturer, you go to the other. Safe harbor turbines might be another one. You have some turbines that are sitting in a yard somewhere that you're not doing anything with. You can put them up somewhere. Lots of reasons. Usually economics, though. Most of this.
Sometimes it's also-
There is another risk. In the US, there are prohibition, can I use this word? That there are certain equipment that is connected to the full electrical system, the software cannot be used from certain countries, so there is a restriction about that. So there are some inverters or even storage facilities or equipment that is coming from a certain country and you cannot use that PPC from that country, so you have to use a third-party PPC for that.
Those are, yeah, go ahead.
Just add one more complexity to that. When you have multiple PPCs, a lot of times you put a master power plant controller on top of it. Now, who handles the voltage control? Who handles the primary frequency response? The Q commands get sent. Are they voltage commands? Where does the set point go? Very complex. Then each has their troop and dead band, and ramp up, ramp down.
And this just from experience. Well, to wrap up your question, just to say that it happens all the time, and it's probably gonna happen more. So I mean, we're almost to a point where if you don't see two, maybe you're like, if you see one plant controller and one model, that's more of a red flag than it used to be. Doesn't mean it's wrong. Yes. Yeah.
PV inverter with on-site battery energy storage.
And we'll see similar hybrid stuff with large loads, probably. But to your point, Ty, this is one of those places where, from experience, I would much rather have a detailed EMT representation of each of the controllers and put them together and connect them in the model space the way they're connected in the real world. Because there's nothing worse than getting, being busy at your work, at your job, and getting an emergency phone call from someone, maybe who's Todd sometimes, because the controller doesn't work. And it's my fault because I'm the main controller. But the fact of the matter is maybe we didn't study it because we couldn't in the PSPD. So it's probably a lot cheaper from the developer standpoint to spend a little bit of time and model it in the EMT and figure it out before you're curtailed for 6 months. Because once stuff gets in the field, and once each of the vendors signs off their equipment to you, getting feedback, getting their input is much more difficult. Like, and this is one of those instances where a really good use case of EMT is this ability to do this control interaction type of study before it hits the field. So, I mean, how much would a study like that cost? Like a controller interaction, just ballpark.
Just within a single plant.
Yeah.
It's not gonna be.
Yeah. And
20 grand.
yeah, and how much revenue do you lose by being curtailed for half a day even? So it's one of those trade-offs, right? Where without knowing the context, you could say, well, I'm not doing that extra study. I don't want to pay that engineer 20 grand or whatever, but maybe saves you millions of dollars, right? I find in my experiences, as soon as you get curtailed and you lose revenue, a lot of leverage happens to get studies done. But doing this beforehand is a really good use case of EMT. And like Lucas said, it's not one of the most expensive things, right? It's more of simple type of study to do. So any PPC questions before we move on? All right, so we're going to talk EMT model creation and benchmarking. And maybe we'll finish it in 40 minutes. I mean, into the open discussion. Maybe we'll see. So just to recap, basically where we've been is most important prerequisite is, do you even need to do an EMT study? We might not need to, but just be sure of it before you go down this path. There's lots of good use cases, but understanding what they are, the limitations of the software, system trends, help you kind of predict how your system's changing and what to choose. They're resource intensive, so if you're doing it, you want to really maximize your benefit by, really scrutinizing the data, doing things like studying controls while you're in there. It's a good way to maximize your benefit. If you're going through the effort of like setting up a full EMT plant model, that's usually the biggest chunk of work, right? And then testing and tuning little sensitivities at the end are one of those incremental benefits that you get. So we're going to jump right into kind of actual model creation and benchmarking. And I'll do my best to stay on time. If I'm way off, we'll finish it tomorrow. But I want to give Lucas time. It's amazing when you do these, right? You start with this morning, I was like, I have nowhere near enough content, and now I'm way behind. It's amazing. So I'm going to skip model validation for now. I'm going to cover model validation in the design evaluation section, which is out of order, but it will probably make sense when we get there because I linked them in my mind. But so we're going to assume for the rest of this discussion that the models for this session that the models are validated. We're just making that assumption now. But what we mentioned a bunch of times, making the model is the critical starting point. It's the building block to your simulation. It's the building block to your study. A little bit extra time at the beginning helps a lot. A little bit of kind of mental procedures help a lot. You'd be amazed how much pain and suffering a missing space or like a wrong comma or a fudge number by accident can cause at the beginning when it's causing a problem that has nothing related to it at the end. So it's really good to have this screening at the beginning. Again, as we go through this, group discussion is good. The developer talk, great. As the experience comes as we go through here. So we're going to leverage, again, the PSPD stuff. Then when we get to model benchmarking, this is one of my favorite topics, so we'll see how long that takes. But it's very good at building trust with models, right? So we have people who don't like modeling and studies say, well, they're all wrong, so why would I try to do that? But there's ways to give us some trust in the model space. There's ways to kind of make us comfortable with doing the detailed modeling and trusting the results. So benchmarking specifically, we get into it, but why is benchmarking important? Well, it'll show you that the model and the product are correct. That's through validation, but benchmarking is kind of a loose term. And also across simulation domain. So if we're doing a cross-domain thing, like studying two contingencies in the EMT and the system contingencies in the PSPD, you probably want some assurity that both models do the same thing. Because if you're not benchmarking the models together, then you could be studying something in the EMT that's highly tuned and something completely different in the PSPD because it's different model not benchmarked against each other. There's probably no perfect benchmark out there, even the best vendors. But a big piece of benchmarking is knowing what is wrong and quantifying what's wrong. So if you just know what you're getting into when you go forward. So it's funny steps here, stepping through kind of getting an inverter model and putting it together. So this isn't a joke, right? We talked about it earlier. The first step is to get an EMT model. It can be harder than it should be. Well, it definitely is harder than it should be, but it can be extremely difficult, depending on who you're getting it from and what the project is and the age of the project. So if you're a transmission system operator, in the current paradigm, if you don't have a requirement for EMT, either in your interconnection agreements or your tariff or whatever, it's going to be really hard to get one at the moment, because without the requirements, there's big variance in if the EMTs are available, what they cost to developers, timelines, things like that. So for TSOs, requirements really, really help. Also for TSOs, your job is kind of tough because you're the ones managing the system over this, the lifetime of the system, which means there's a lot of old equipment out there, right? And a lot of old equipment might not have an EMT at all, like we talked about earlier. They might not have an EMT model in the right version. It might have a different model, but no EMT because they didn't build it in the code. But they may not even exist, right? They may be manufactured out of business. So really important when you do retroactive requirements. So try to cover the balance between getting new EMT models for new plants and making a burden on everybody else for a little benefit. So for the developer side, getting your EMT model during the interconnection process is one of the biggest pieces of advice I can give you, having worked at a manufacturer where you'd be really surprised what you'll get for free if you say, I'm not buying your turbines unless you give me it. It's really great. Don't tell them I said that. But it's a really good way to get it, right? Especially with EMT models. It's kind of a problem that's going away a little bit. But when EMT models were first starting to bubble up, to make a good EMT model requires a lot of R&D, and manufacturers like to recoup R&D costs, right? So the costs in general have come down, so it's less of a problem, but also really important to use your leverage as you get it. Because once you sign your interconnection agreement, once you've signed over the equipment, if you don't have anything in your service contracts for EMT models, then you're basically going in fresh with a new product request, which has costs and a new contract, a new stakeholder. It's just wild. So really good idea to get those as soon as possible as part of the package. Part of your fleets as developers may be older equipment. You might have mixed sites with brand new inverters with EMT and other ones with old inverters that may not. So weird nuance there for study space. Retroactive requirements can have a huge impact on the developers. So if I ask for EMT model for everything, then we're talking maybe 2 years, hundreds of thousands of dollars. And even when you go, and I've done these before, even when you go and ask for a piece of old equipment's EMT model, even if you're spending a bunch of money and you're waiting 2 years, someone's guessing probably on the back end, right? There are literal products out there that the code doesn't exist anymore. So you basically have old test reports in like a PDF format that you're kind of eyeballing. You might have, code in Fortran that you're transposing into C. Just a lot of the times this old equipment, there's no easy mapping like we talked about earlier. So it's a best guess. You're getting something about representative, and best guess is, again, if we're doing a detailed EMT study, best guess kind of erodes the benefit of doing the rest of the study. For OEMs, there's a cutoff where the design practices before which making EMT is really difficult, right? So after a certain period of time, a lot of controls got really well documented, and there's actual maybe block diagrams, maybe code snippets, things like that. But before that, there wasn't a lot of it, right? So especially with type 1 and type 2 machines for wind, really old inverters, there were very few modeling requirements and practices. So asking for something from that vintage can be very difficult for the manufacturers. For grid requirements, because of the nature of regulatory aspects, and the fact that a lot of stakeholders, the ones in the room aren't the problem because you're here listening and learning, but a lot of stakeholders know about a requirement after it's enforced, which means a big portion of the industry finds out something at the same time. And if everyone finds out at the same time they need an EMT model from the manufacturer, the manufacturer has 100 requests in a week, where they get once a month usually. So, and that adds to the whole perception of models being bad and things like that, because it's just, this endless cycle of that. So, again, I mentioned it, but when you're making an old kind of bespoke model for something, it's completely out of normal business practices. It usually comes with a really high price because it's just a one-off. Usually the folks at the manufacturer who are doing these are the guys who have been there for 30 years, who actually wrote their controller back then, and their time is super expensive. So it's just very difficult in that way. So for all of us to keep in mind, like I mentioned, getting an EMT model early before COD is best. Adding your modeling provisions into your service contracts is also really great, especially in EMT where different compiler changes, different software changes, different software versions, Windows things require updates. Windows updates might require model changes. So having something in your kind of service contract for models to say, if something changes, give me an updated model is very useful, or else you kind of stuck in the cycle of asking for bespoke models all the time. And keep all of this in mind in the kind of points of view, everybody, when we talk about making model requirements, if any of you are involved in those type of modeling requirement discussions. So step 1A, you have an inverter, but also you need a plant controller model. Obviously, they have plant controllers that need to be modeled. They're doing all the normal operations pieces. They can be provided by the inverter manufacturer. Depending on the manufacturer, they might not in your area. So if you know that, if there is one, keep that in mind. You also, because of the way that some of those example cases are set up, you may have a third-party plant controller manufacturer who's supplying you for the site, but you may also get a model of the plant controller from the manufacturer because it's part of the example model. So knowing which one's real and which one isn't real is really important when you're getting these models. If it's written from a third-party consultant, I know there's probably a lot of us who work with them, but it's a very different world between writing plant controls and communications for the real world and putting them into a model. A lot of these third-party consultants don't actually have modeling staff. So then they kind of write the controller diagram, they give it to modelers, and modelers try to transpose it in there. And it really leads to a lot of opportunities to mess up throughout there. So knowing what is there, what's supposed to be there, who the manufacturers are, and what their models may look like is super important when you're reviewing a plant controller model. But it's really similar to the kind of inverter model acquisition kind of steps. Do they actually make a controller for what they're selling me? What is the actual full control capability of the facility? What's there? Who's communicating? How are they communicating? Who's in charge? And what communication protocol is used? And do the additional devices actually use it? Which is another way. You'll find out quickly if you're trying to connect a bunch of controllers who don't have the ability to talk to each other in the model space. So the first two steps were just getting a EMT model. This is getting the right EMT model and power plant controller model. So again, mentioned it before, but just because it's EMT domain doesn't mean it's good. People make errors in any tool, with any tool. There's a lot of non-technical stakeholders involved here. They're all operating between us nerds, right? And we use a lot of jargon in the industry that is different from their jargon in their industry and their stakeholder set. So very important to make sure you're asking the right questions for the right manufacturer, for the right equipment type. Otherwise, you very easily can ask the right question and get the wrong value that looks right, and then you're still wrong. The right EMT model also is site-specific for the equipment, site-specific for the subversions of the equipment. Is it a platform 4 megawatts? Is it 4.2? Is it a Mark A, a Mark B? Very important things to compare and contrast those things against your interconnection documentation. Is it the right firmware? A little loose. You'll find out the hard way if it's the wrong firmware. But it's a little hard to catch at the beginning unless it's like super old, right? If it says 2006 in the firmware version, you probably have old firmware. And then the plant-specific representation piece. So if you're getting like I said, if you're getting a model directly from the manufacturer, they don't know what your plant is. They don't care what your plant is. So they're obviously not representing your plant. So please don't just take that model from them and submit it to the interconnection case. Don't take the model and just because this is an ERCOT specific example, but there was a while where literally just part of the, they weren't doing EMT studies, they said, just give me a model. So there was no scrutiny on them. So basically it was just, I'm getting an EMT file from a manufacturer. I'm dropping it in the RSAW spreadsheet and the EMT thing, and it's stored there and no one ever looks at it. And then 5 years later, they want to do an EMT study, and then they contact me when I was working at a manufacturer, and they say, here, we have a model for this plant, and it's just a generic model. We hand it out for everybody. So really keep that in mind, that you need site-specific parameters, site-specific collector systems, site-specific controls. The manufacturers, a lot of the times, don't know what controls you want. They don't know what area you're interconnecting. Sometimes they do. They don't know what the balance plant is, the actual other pieces of equipment. So you have to make sure those are site-specific.
But it seems like you're putting a lot of onus on the transmission provider who they're interconnecting to, and not as much on the developers here to go and review all these finer points of the system that we really don't have knowledge of.
This is for everybody. This wasn't just for the transmission providers. This specifically is mostly a developer, these slides. Yeah, you guys you're taking a model, you may do some screening, but y'all should be able to know or trust that what you're getting is pretty close to right. So these aren't intended to be for transmission providers. This is for developers and consultants who are reviewing the data for them. But for some of these are things that even the transmission operator can just have in mind, and just as you're scanning through something to catch quickly. So giving the information here just for everyone to know, because if you know that at the transmission side, and you can just glance and see, oh, this has no plant controller, and that's an easy way to screen it. Then you just send it back. And that's another thing to keep in mind here with modeling and model checking is it's not the transmission provider's responsibility to check wrong data. It's not your responsibility to fix wrong data. It's wrong to send it back. Because there's a flip side where, especially in the NERC side of things, when we had this conversation at the IRPS level, where there are service providers who say, I need full source code, I need full block diagrams, because I need to be the one to fix all the controller interactions and problems, which is not the way it should be. Because one, there aren't enough transmission service provider engineers to do that work for every interconnection. They're not the experts for each piece of equipment. And it's just not their responsibility, right? It's the interconnection customer's responsibility to give accurate data. So it's fine to review at a high level and flag it and send it back. But you don't need to be the ones who are actually testing and tuning it. You probably shouldn't be either. Because as soon as the TSO or transmission service provider changes something, it's not what was submitted anymore. So the best way to do it is just send it back. That's what I would say. When I was in that position, I was a curious person, right? So I would look into it and say, hey, I think this is the problem, fix it. And that would be the kind of middle ground. I would never fix anything without telling them. But yeah, most of the discussion is for consultants and developers, but it's still useful information for ESOs. Any other questions? Let's see. Yeah, site-specific, really important. Well, I already covered the last piece, so okay. So getting the balance of plant data, the manufacturer is not the person to ask for the balance of plant data. The inverter models and the plant controllers are just pieces of the whole plant. So you're taking the drawings and the data and you're putting those into the balance of plant. We talked about it a little bit throughout. But the big thing here to keep in mind is goes a little bit against what I said earlier. But if you're asking for data and having a standardized checklist helps. I used to have a standard checklist, but break it into categories, for different types of studies. But it's really hard, really easy to just forget to ask something to someone during a data collection. And it's really easy to forget when you're in the process of sending data back and forth, but I forgot to ask something because I'm just in and out into data and data review. So reviewing the data balance of plant data, a little bit artful and comes with engineering judgment, but for those of you who are taking this information or turning it into or have received something from someone who's built this model, just some guiding questions. Did you get everything you asked for? Do the values make sense? Really comes from judgment, unfortunately. There are some kind of guiding things like that, but do the values make sense? Is the data have a date or a version? Very important because there's a lot of times people are doing same study and different versions of the same data. Does the balance of the plant data match what was in the PSPD model? So we're at a point in the industry where most of the facilities also have a PSPD model. So seeing if it's the same balance of plant is a good way to check to see if the EMT model is what you expect it to be. That's equipment type, manufacturer type, supplemental devices, all that kind of stuff. The big one is, have you seen the data before? If you're expecting site-specific data and you've seen this exact same data before, it's probably not site-specific. Or someone copied and pasted it from somewhere else or vice versa. Putting all the pieces together, this is more just to read through later, I think, and we're late already. So the big pieces of putting all the pieces together is understanding where your responsibility ends as the model builder, as the developer, or the consultant. You don't care about the transition system, you're building up the point of interconnection. If you're a consultant and you have a specific piece of the work, knowing where you are ending and where you connect to others is very important. Balance of plant data, it's coming from physical representations, drawings, cut sheets, things like that. But make sure they fit together the way they're supposed to. Spot checks are really important. Solving your simulation as you put the models together is really good for those of you who are building EMT models. Solving when you can and when it makes sense in little blocks, because it's much easier to fix 1 or 2 errors at a time than it is to build an entire plant and then you have 100 errors with different interdependencies, and it's just a mess. And then once you solve it and you can solve it and you replace where it runs and you get actual values, do the losses and things make sense. If you have losses of 100 MVA over or MVAR over a transformer, maybe you have the transformer model wrong, or vice versa. And then doing other types of node disturbance runs or thoughtful checks throughout the process, however you like to do your work when you build your EMT models, is really important as you're putting the pieces together. Site specificity, too much talking for big words. I should have put that at the beginning. Very important as well. We already talked about it. I'll hammer it home again, right? But parameterization. So you could have a model put together perfectly, exactly represented as it is on site, but you put the wrong control parameters in. Then you have a wrong model. But parameterization is really important and linked to documentation, usability, and fidelity and mapping. And that's in the software tool and also the software, the EMT model, right? If you don't know how to use it, how to open it, how to access the parameters, you can't map them. If there's no mapping, how do I know what value goes where? If the fidelity of the model isn't there or the software doesn't allow you to access those things, I have nothing to map, right? I can't map a real world parameter to a model that doesn't have the fidelity that includes that parameter. There's a lot of stakeholders involved in the site specificity piece. A lot of times this is where you get a little bit of back and forth between the developers, consultants, and the utility or the system operator, because the system operator has in mind what your voltage should be, or sorry, voltage slope should be, what the deadband should be, your voltage schedule, things like that. Frequency droops, deadbands, all of those kind of real world discussion pieces, what the utility wants, they are going to inform drastically your site specific settings. Which is another way if you're a consultant or a developer or a transmission system operator to kind of get a feel for if the model is good as a gut feeling. If every plant that connects to my system, I say you must have a voltage schedule of X or a voltage deadband of X, and I get something that's completely off, then that's either a real big error or a wrong model, or an error that I'm asking follow-up questions in there as well. So what do you do when they don't make sense? Site-specific data. You can either change it and tell someone, or you can suggest it and tell someone how to change it. Or a lot of times it could be just a miscommunication between the two, and then a simple question fixes that. So basically, all I have to say is this is a collaborative, iterative process when we're trying to get this data. And it comes from experience from all the parties. Like if I'm a consultant and I'm saying, hey, which control mode should I be in the US? And someone says, fixed power factor mode. Probably the wrong answer. So I'm asking someone else or asking a different question. So representing site-specific controls, we hit on it a bunch of times throughout, but this is a really strong use case for EMT. You can do these model details. You can catch them before you're in the field. You can catch them before it's actually in the ground and you're running. And the reason why that's important is that a lot of times these weird stuff, weird control interactions, weird kind of performance within the same control band, they're usually happening at weird bookends of performance, right? So it's very possible that you may have perfectly tuned controls and communicated controls during all of ERCOT's model quality tests and your interconnection tests and all that. And then there's just some condition on the system that puts you towards some operating point, and now you're oscillating against each other. So catching those things and running those different tests and things is very important, and kind of bookending as well. So model benchmarking, why model benchmark, and what is it? So this is my definition. There's probably other definitions. There definitely is other definitions, but just simply put, comparing a model to another model, or to the performance of actual. The last piece is technically model validation, but I say benchmarking. I'm probably wrong, but that's what I say. So the big piece that we're going to talk about in this one, because we're talking model validation at this point, wow, certainly, is software to software. So we talked about the co-simulation aspects and the benefits. A key to doing co-simulation is benchmarking between models. And that's just to know that I'm apples to apples, right? I'm not doing something completely different in two different software. So model to measured performance, just briefly here, model validation is part of the type testing process. We'll talk a lot more about it tomorrow. But basically what that does is just shows the difference between the measured response and the model response to the same tests, right? You're setting up a test system, you're doing tests, you're measuring, and you're doing the same thing in the model, and you hope they match. They're never going to match perfectly. The perfect model, perfect tests, even if I spend weeks mitigating measurement errors and things like that, there will always be differences. And this is true also between softwares, because similarly to how, the models are always interpreting and calculating things and estimating. So similar to how their, measurement devices in the real world and the lab bench will operate differently than measurement devices in a software, and then, measurement errors and things like that. There will be differences. You'll see differences. There's never going to be a trace on trace, probably. But the good news is they show them to you, right? You do benchmarking, you have a report. You very clearly see for tests, 1 through 10, there's a weird hiccup here, but I can explain it. So the reason why test benching and test benches and model validation is difficult, and why benchmark between softwares is extremely important. I think I put it on the next slide already by accident, but the important piece is that the test benches, the actual laboratories for going and putting your piece of equipment in and testing it, they're few, they're in really high demand, and they're pretty expensive to use, right? And to do a proper model benchmarking or model validation, you're doing extremes, right? It doesn't really help to do a small voltage step. You really want to do faults. You want to do deep faults and long faults and scans of certain aspects and things like that. You're not doing that in the field, right? You're not going to drive a container up to there and start testing those things. So because of that, it's really important to benchmark against software to software. So most of the time when you have a validated model, the OEM will validate the EMT model against the performance. And then you can kind of treat that EMT model as your source of truth. And there's a couple of reasons why I'd say that it's a big kind of leap, but we'll talk about it, is the other piece about the test benches being in high demand is that you can't sit there for months and test every single permutation of parameters. It just doesn't make sense. So most of the time it's one platform of product and one set of parameters. So if you benchmark one set of parameters against a model with the same set of parameters and you match the code together, then the logical step is if I change the parameters in the EMT, the validated EMT model, I can treat that as a new source of truth, but with a different parameterization, which is a little bit of a leap, but we have to. So what do these look like just generally? I know I said there's no trace over trace, but it also brings us to the other point, which is Zoom really changes the perception of a benchmarking report. And I covered up the thing that explains that. But you'll see at the very top, right? So this is just a regular active power reference change. You'll see the middle one looks really good, right? They set the reference. It changed the active power in the same way, same rate of change, same amount. There's a little bit of mismatch at the very bottom where it hits its set point, but it's pretty good, right? So this is kind of an example of what it looks like. Zoomed in pretty good, right? But if you look at the top one, you'd say, well, that's a huge mismatch, right? But I covered the scale, and the scale is really tight, right? So it's just really important for folks who are reviewing benchmark reports, who are making benchmark reports, look look at the scale, look at the axis, because a lot of stuff, I can make any benchmark report look any way I want by changing the scale. So that's active power rate change. This is reactive power rate change, and you see a little bit of mismatch here. So you'll see the actual Q at the bottom is about the same. You see there's a little shoulder in the measurement that isn't quite captured the same way in the model, but you also see the top piece, which is where measurement error comes in. So you'll see they're pretty close, but they're offset by equal amounts because there's measurement error there. And again, the scale is really small here on this. So this is what it looks like. This is 2 of the simplest tests. Most model benchmarking reports are thousands of tests, but it's a manufacturer responsibility. The transmission service operators put it on the developer put it on the OEM, you'll get it, and then you can read it and see. So the other piece, this is a phase jump, which shows a little bit more actually. So if you look at this, it was just a good or bad model, right? It's tough, right? Our initial instinct is to say, I want everything on top of each other all the time, which is a good instinct. But knowing what's real and what's wrong, and how the actual model and the real performance of the product works is important. So in this case, you could say, hey, the shape's about the same. The initial point and the finishing point's about the same. That's pretty good. The transient's different, right? What I would ask is, if I'm getting a benchmark report like this from a manufacturer developer, I'd say, explain to me why this is different. And it could be something as simple as time step or sampling, or the simulation domain, or the calculation errors, or the limitations of the software you're testing it in. So this is to show that this is a good model. This trace doesn't look good, but these are explainable differences. And this is the type of thing that the benchmark report susses out and lets you get information on, so that you know the limitations of when you're doing these things when you're running it. So between PSPD and EMT, we're assuming the EMT is validated. The best part about the validated EMT model is that the manufacturer does the work for you. You're not doing the work as a developer. You're certainly not doing this report as a transmission system operator. The validated model is validated against actual performance and tests, and usually you'll get explanations of real differences. If there's a real difference and it's like an actual big mismatch, you'll get an answer like, this is a rounding error in the measurement. This is a real performance. This is a limitation of the model, because those do exist. There are some things that are limitations. You just explain them, and then the model's still good, but with the caveat, right? The negative here is that you're doing this on one platform, one specific parameter set, like we talked about. And we need, as an industry, a way to represent in different domains the actual site-specific parameters. And there are no sites. There's no IBR facility in the US that has default settings from the manufacturer. There's not a thing that happens. So we have to have some sort of source of truth. Usually that's the EMT validated model, because you're doing thousands of tests, every control mode. It's pretty good certainty there. But like any software, there are bugs and hotfixes and things like that. So keep that in mind as well. So the kind of process would be the base validated EMT model. That's the actual on-site testing and model benchmarking, model validation, checking test over test, sample over sample, explaining differences. Again, that's the one parameter set on one platform starting block. We take that as a source of valid response and trust in the control modes. We move it on to additional validated EMT models. So this would be an EMT model that has different parameter sets, or a slightly different set of default parameters. But keep in mind, there's always going to be bugs, always going to be hotfixes. And this is another place where it's very important to validate the EMT models and have the visibility into the detailed controls, because some EMT models and products are so intertwined that you can actually find product bugs in the validation efforts, right? I've done it a few times in my previous roles. I was one of the few folks with source code access in the US for the manufacturer, or the only one in North America who had that access. And it was, we're doing a model thing, we're in the EMT model, we trust the model so good that we dig into the model code. And it turns out it wasn't a model problem, it was the code of the actual product. So we did this validation piece, and the link was so good that we caught it we call it a real product issue with a validated EMT. And this was in a control loop that wasn't even part of the type testing, right? So it was a different additional control loop that was new, and we still were able to do this process and get back there. But those types of bug finds and hot fixes are why it's really important to have a user-defined model for these and for EMT and for PSPD, because a bug in the product, you're not going to get a fix in a generic model ever, right? Because it's like 8 years and they're not representing that control loop anyway, or control feature. Anyway, so you take that EMT model, we're assuming it's valid. We're going to put software bugs on the back burner of our mind for now. Then we're going to put site-specific parameters in there. So that's your site-specific frequency droops and voltage slopes, things like that. And now this is your source of truth. This is your most accurate representation of your EMT or of your IBR plant, and that's a site-specific EMT model. That's our new basis. As we transpose this model into PSPD, we want to make sure that we're putting both those models, the PSPD and the EMT model, through the same exact tests, same test procedures, same test bench, same impedance, everything identical, and also matching the performance between both, mitigating errors, and things like that. So there may still be differences in performance. A lot of the time, the differences in performance between EMT and a PSPD are going to be in the really fast transient times, the really fast squiggles, if you want to look at the graphs, because those are where kind of the PSPD simulation engine breaks down, and the detail of the EMT it really shines, right? There's also differences in just the nature of doing things between two softwares. Things solve differently, even between two softwares in the same domain. I can run the same test on a same model in, the PSPD softwares, PSSE, TSAT, PSLF, just to name 3 of the major ones in the US. I might get the different results. Same model, 3 different softwares, different results, because it's a simulation engine. That doesn't mean it's a bad model. It could just be a weird nuance in the simulation, right? And a really good example of this is when you have voltage right through, and the voltage drops, and the terminal recognizes voltage below the threshold, it's going into voltage right through mode, and it has to come out of voltage right through mode at the threshold, right? So if the threshold is 0.90 per unit, the model could be perfectly set up to tune to get out of the voltage right through mode, but 2 simulation domains, one may solve to 0.9001, and one might solve to 0.8999. That's pretty close. That's 4 decimal places, right? But you're on either side of the threshold. So that's a very easily, that's not a model issue, that's just a difference that you explain. And then you've proved that by just running slightly different to bump it out of the threshold in bandwidth there. So the important piece of this is that you're never going to get an identical EMT and PSPD model for everything, for every test. But if there's differences and you're uncomfortable with the differences, ask someone about them and you'll get an answer from that. All right, and then we're just a little bit of kind of discussion here, because this is, we talked about this benchmarking piece is mostly parameterization and testing and control parameters. There's another piece of benchmarking that is really kind of missed and is a really huge driver for a lot of differences in like studied results between platforms and different people doing different studies, is the balance of plant. It's a lot of the time an afterthought. Even experienced study engineers, they're taking a PSPD model, they're just throwing it through a conversion tool, and they're popping it in the EMT software, and then you see the difference, right? And then they don't check, right? And they're just running it, and then they did that kind of thing where you do all the steps at once, and then you can't kind of dig into the details, right? But it's very important to actually take the time outside of the dynamic piece and just solve a load flow in each. Because you have very different, there's a lot of places for things to go wrong. So what I usually do is I'll start from an inverter and go up. And just kind of, we talked about the single machine infinite bus. I kind of scooch that out and test each little section at a time, right? Or you could build the whole thing and solve it in both softwares and check. And the main places you're going to see differences that you want to check, really simply, and first is just check to make sure the inverters are giving out the same amount of power and reactive power. If those are different, something's wrong. Really easy. You want to check the losses on the transformers. Make sure the losses are the same. This is just a quick visual check as well, right? If you see anything wrong, you're digging into values. The losses over collector system segments, the losses over the main power transformer. These are all places where you might see, you probably likely will see a lot of variance, and then you're digging into it. So this is just to show that, like, and to really focus us on the fact that we talk a lot about EMT, we talk a lot about PSPD and the detail of the models and the controls and the software code, but I want to make sure we don't forget the actual balance plan, the things that connect them together. So, and just as an example for this one specifically, we did some work when I had a presentation at the IRPS, and a manufacturer went and reviewed their models versus like their own site models with site specific in their data versus the planning models. And I think they did 20 or so plants, and not a single plant had the correct balance of plant for one reason or another. And that is most of the time main power transformer impedance issues, missing OLTCs, unload tap changers, things like that. So very big opportunity for a mistake. So I'll close this off before we get into the discussion piece a little bit, because I want to close this off with a little bit of a case study for success that kind of puts everything together to kind of show the benefit and what's possible, because it's been a lot of theory and a lot of nebulous things, but seeing an example straight up, I think is helpful for this. So this is a study I worked on when I was in one of my previous roles, and I'll just get into it quickly, hopefully. So this is one of those times where I got a call at 3 a.m. because someone is pissed off, which just happens when you work for a manufacturer and you're in that role. But what was happening was essentially the facility showed instability that was in operations because it was never seen in the study space. So it went through the interconnection process, perfect, flying colors, passed every test, perfectly stable. But as soon as it went into service and a certain set of contingencies happened, we had this instability. When that happens, most of the time you get curtailed. That's just what happens, right? You get curtailed to an amount that you stop doing the bad thing, right? For that system configuration. 50% in this case is not bad. A lot of times you just, you're opening your breaker till you fix it. And then the solution for this proposed by the utility was transmission assets. And I think I listed what they were in there, right? So very common thing. We probably all have seen, consultants have seen it, developers have seen it, whatever. So in the current paradigm, or the old paradigm, I'm saying optimistically here, is that we would say, hey, we really trust the study process. Models are the best representation we have. I guess I'll eat the cost and I'll build the transformer. Sometimes, a lot of the time, right? We're trusting that. The new paradigm is look into it. Leverage the things that we talked about this morning. Understand what where you are connecting, the conditions of the connection, how your facility was studied and why, with what representation and what detail. And what we did was we performed a detailed analysis using really highly representative models at the OEM with consultant help, and we avoided the transmission upgrades entirely. And we did it. We solved this curtailment issue and the contingency issue with just some tune controls. For those of you who came to Florida, sorry, we're talking the same, but this is more formal about it. You kind of got the cliff notes in Florida. So first things first, basically, was the problem, right? They were curtailed, huge. So they're both curtailed until the transmission upgrades were completed, and they were assigned the cost for those transmission upgrades. So that's a lot of money, right? That's years of half power curtailment. That's a whole substation reconfiguration, a new 138 kV line, a new StatCom on the grid, and project curtailment for basically almost every first contingency, which those are all like Todd probably wakes up with sweats, cold sweats in the middle of the night if this happens to one of his facilities, right? Many developers do the same. So what was happening specifically, and this is one of those things I was talking about earlier, which is the post-contingency SCR, if you want to use the metric, was 1.75. Low, right? We're well within the specialized tuning, and this shows why. All the other contingencies, fine. This was a system configuration where it got really weak, really radial for a first and a second, a first and a couple seconds. So And we also saw 20% voltage swing. So I think you asked, what does weak grid look like? This is what weak grid looks like a lot of the times. So this is what you see the massive swings in and out here and the kind of cyclical nature. This is because the grid's weak. The controls were parameterized, the gains for the ride through were parameterized for a stronger grid. So there are high gains, high magnitude response, which means that in a strong grid, that same response maybe got a little bit of voltage deviation, a couple percent. In a weak grid, we're 20%. So same tuning as a strong grid, works perfectly in strong grids. In this 1.75, we're literally swinging up and out of the way. We're literally swinging in and out of voltage ride-through modes. So you hit under voltage ride-through at 0.9, you freak out and you're in ride-through mode and you crank the other way. And now you're up above 1.1, which is the other threshold, and you just cycle. You're literally driving yourself in and out of ride-through mode because the grid is so weak, and you're tuning, and you're doing this controller interaction. And you can kind of see the same with the P and the Q. So you keep trying to recover curve power with this Q response, and you keep hitting a voltage collapse. And that voltage collapse is driving the re-triggering. So this is a very normal, not very normal, but you see this and you know it's weak grid. This type of re-triggering is very indicative of weak grid. This is for two contingencies. So what do we do? Well, the first thing I did was I said, give me the model you used for the study, which was a generic model, of course, right? But luckily, this was a brand new facility, or a year old or so. We had all the models at hand. The first question I asked, what model did you use? Second question was, why did you use this model for this interconnection point? And then we argued about it. And then we ended up doing a detailed study for this thing. So basically what we did was this, and this takes a lot of, I guess it's a better word. I got in a lot of trouble for going this, but it worked out. Because a lot of times the easiest thing to do is just say, the customer's fine, we'll do what they say, whatever. But I wanted to make sure this is a real problem and fix it. So that came up with several meetings with the customer to explain to them that we can probably solve this without a transition upgrade. Because the phone call is, you guys messed up, now you owe us millions of dollars for this transition upgrade. So we say, maybe we don't, let's figure it out through here. So that's customer kind of talk and kind of getting them to buy in for this alternate solution. The other piece of that is collaboration with the regional entities, the transmission service providers. And luckily for us, we had some folks who are really willing to work and give us a chance to test this out. So the reason why you need that detailed coordination with the regional entities and the service provider is I don't have access to the system model. We talked about it, right? Even in phase domain, I don't have access to system model because at the time I was at a manufacturer, and manufacturers actually, believe it or not, have less access to system models than even consultants, because I think we're going to use them for market manipulation, but probably that's a good concern. But we have less access. So I had no access at all to the system model. So I had to get information for them. And part of that was actually going through NDA processes to get what I needed was the reconfiguration of the system afterwards and the system strength. And those both needed NDAs, which again, makes sense. And I had to show them that there was technical justification to actually reperform these two contingencies in the EMT domain. And we kind of settle on this fix in EMT and check it in the PSPD, the RMS domain. I don't have them in here, but we did full benchmarking between the two. They were on top of each other. It was great. So we had all that. We got the system data. This is the one case and I agree with Lucas that you shouldn't do this, but we had to. We did a weak grid study without the system. We had to. We just kind of used the SCR we got from the utility, and we also looked at the event reports because you can kind of estimate the system strength and impedance by seeing how much voltage changes at the point of interconnection based on how much reactive power is changing at the plant. So you can kind of estimate. It wasn't perfect, but we got there in a roundabout way. So we have all the access at the manufacturer. So I went and we downloaded all the parameters, the firmware versions, everything. We created as-left models of the actual site as it was installed on site. We recreated a very small region of the grid in in EMT. This is an old slide, so that should be EMT. But when I say small, I mean like one line. literally one line out there. So very small, that's all we got. That was what the NDA was for. So maybe it's not just SMIB, but it's essentially SMIB with a impedance in between. We netted everything else out, even neighboring plants, and we had to benchmark it again against the positive sequence. So the worst planning events we studied in the EMT because they were the ones with the 1.75. The other ones were fine to study in the PSPD. We changed a lot of parameters in the plant controllers to make them operate correctly. And also we had to change inverter control parameters. And one of these parameters was, if you've ever seen the really sad photo of the burning wind turbine, it was that one, right? So we had to vary, because of the way this active power ramp back up was causing the voltage to drop, we had to slow that down. When we slow down recovery from faults, you end up getting really high currents and high temperatures. I think it's really dangerous there. So that was one of the pieces that we tuned. We were able to come up with a tuning solution for these two contingencies. Because of the way we set up the models, we were literally able to just drag and drop in and out of the PSPD and EMT. Actually, back then I did it manually, which was awful, but now you can do that. But basically, I had to sit there as the expert and actually transpose 100 or so mapping back and forth, which is not fun to do. But we mapped them back and forth, so we had basically a twin EMT in our PSPD model. And we also studied the actual parameter changes with the real experts overseas who built the product. So it was basically, hey, we have a tuning solution. We touch stuff that usually needs review, and they will go there and do like a finite element analysis, all the temperature stuff, the real detailed design work to make sure we're not going to blow anything up by doing this. And the big piece was, since we made the digital kind of twin here of the model, we gave it to the regional entities consultant to run the full system contingency. And that was an iterative process a couple of times, because the first two of our simulation or our tuning solutions caused problems for other contingencies, right? So a couple iterations back and forth between the mapping, we were able to get there. But that was only possible because there was an ability to map back and forth. And we cannot do this in a generic model or without EMT specifically. Could not have done this without the EMT. And then afterwards, we put the exact same parameters back in. And this is what the stable response looks like. So the main thing is, I mean, it's still wobbly, but it's 1.75. But the main thing here is that we slowed the active power recovery while massively increasing the reactive power response. And this was because we were basically voltage collapsing the radial system we were connected to post contingency. So we wanted to prop the voltage up with reactive power while also slowing down the active power to slow the voltage collapse. And that was the solution we came up with. And this is what it looked like. So is this the last one? Yeah. So basically what happened was we did this. I don't have the plots in this presentation. They're out there somewhere. I just couldn't find them. But this exact event happened like 6 months later or 3 months later, which never happens in the study world, or at least you don't see it. And we put the event on top of the new model response, and it was within 1 or 2%. So it showed exactly that it matched, and we did the right process. So this is what it can look like if you have someone really annoying like me as a study engineer, and the willingness of all the stakeholders involved to do it. Those are the soft skills that are really hard that we need the background for EMT to push for, right? Because if we don't know how these all work together, then we're all just doing our own work in our own little silo, and we never actually help the whole thing as a whole. So this is just a kind of an example to wrap us up for the content today before the open discussion. But it's really clear indication that extra work pays itself off. This example was not doing the extra work at the beginning really hurt because that was, in the context of power systems, it was a cheap study, but the curtailment was the extreme cost because that was maybe 3 months of curtailment at 50%. And it could have been transmission upgrades. So doing your due diligence now, and this is for the developers and the consultants, well, the consultants will make money on it either way, but for the developers in the room, doing these studies at the beginning is very important. It may seem like a sticker shock for the cost of the study, but the implications get more and more as it goes on, right? The perfect study is, even all the costs of the perfect study, everything done bespoke by a very senior engineer is still less than like a week of curtailment. So just keep those kind of values in mind. When I started at the OEM, I said, hey, we could charge for this because it came from consulting for the studies. And he said, I don't care. That amount of money means nothing in the context of a wind farm. So they'll do the studies for you. It's just very important to do that and have the ability or have the wherewithal in the context to do them at the beginning. So small mistakes early, really difficult to track down, especially if you're doing a bunch of steps at once. Or the really kind of scary thing is mistakes that don't look like mistakes. Like a wrong parameterization that looks perfect. Because then you end up with situations like the example we showed where everything was fine and then it's an emergency in the system, which means the planners and the system operators, they're not expecting this thing to happen. What's happening in the real world is nowhere close to what was actually studied. So ensuring one thoroughly vetted source of truth is critical. That doesn't mean there's no OEMs in the room, right? That doesn't mean extra work for you in the room. It's extra work for the manufacturers. Because they're the ones with the actual equipment and expertise. They're the ones with the test bench. They're the ones running the thousands of tests and the IP to run the tests. And they're the ones that you can ask those things for, right? Because if you ask for them from everybody, they're going to do it because their competitor is going to do it if they don't, right? So getting those things and putting the work on them is very important. And that's me as a former OEM, because it'll get done, right? The grid connection and the grid reliability is more important than not doing an extra study or an extra benchmark report. So while a lot of the PSPD modeling principles can inform the EMT work, all the extra details make it more difficult as we go through here. And we are really kind of underscoring the importance of engineering judgment, which we'll get into a lot tomorrow and Wednesday. But this today was mostly context and engineering judgment of the soft side of it to inform the rest of the EMT work, because we want to avoid just falling into a hole of just being an EMT studies expert who doesn't know how their work fits in to everyone else. And this really underscores, again, the detail and the kind of quality that goes into the example and the takeaway is mentorship within organizations, training of people, knowledge sharing, and things like that. Because this is something that there's a lot of folks who have had really good experiences with mentorship, some who have not at all had any mentorship, and it's very different between company to company, and it's really hard to standardize that as well, because folks who had a great mentor say, we don't need to actually formalize that because I had one, and then other folks who had none might see that. So again, to underscore today is just a lot of context, a lot of nuance, a lot of interconnected pieces, and it's really important to train up in organizations and mentor folks and learn from each other and from inside.